Hey folks, welcome to another video on weekly paper reviews. I know I haven't made a lot of videos in the last month or so because there really wasn't anything exciting. Well, this week there is this paper and the LLAMA 3.2 releases. So we'll first talk about this paper and then get to the LLAMA part. So this interesting paper came from Google DeepMind, where they train language models to self-correct via reinforcement learning. So self-correct means that the model has kind of realized that there is an error and it tries to, well, not exactly the model has realized. Well, you tell the model that, hey, you've messed up, correct it, and the model corrects it at the end. So that's the kind of paradigm that we're looking at. Let's start with an example. Okay, so here, this is a problem, a math problem, and the model generates an answer. And then, of course, this is wrong. So we basically give it an instruction that, and the instruction is very generic, right? Like, it's not specific about like what went wrong. The instruction is, there could be an error, please correct the error if any, and write the solution. So in the second turn, if there's an error, now again, this is I mean, in my opinion, it is hacking because the first turn could be correct, right? So you give an instruction to possibly correct errors of the previous turn. So if it's already correct, you don't want it to change in the end. And that's what the authors also address. And it corrects in the next turn. So, okay, so what is the best way to make the model do this? And what the authors find is reinforcement learning is, or rather, some version of reinforcement learning based training is the one that works better. Naively, you would think that SFT should work, but it kind of doesn't. So they first do some SFT where you give it some prompt and you compare or compute loss on either the first turn or the loss on the second turn given all the input of the first turn. And they compare against with the reinforcement learning, and they say the reinforcement learning strategy is much better. So let's very briefly review what they find. And again, if you want to know the details, read the papers. This is just meant to be a lightning summary of these papers. So I obviously won't go into a lot of details because I don't know that. So in their setup, what they do is first they do SFT. And the way they do SFT is, let's see. Right, so they construct a reward function to see, because the outputs could be varied, it's hard to create, let's say, a next word prediction objective. So instead, what they do is they decide to do a reward model based. So the reward model will tell you whether the output is correct or not. And what they do is they'll just compute the loss on the reward model outputs. Basically, they'll pass the outputs of the language model to the reward model and see what the outputs are. And this is the kind of loss function they would have is, they will sample, given a prompt, they will sample an output and then maximize the reward function. Obviously with the constraint that you shouldn't deviate too far away from the original policy. So let's first look at the SFT results. And the key question they ask is, can a base SFT fix these things? And basically, and they try two different SFT techniques. Won't go into that, but basically what they find is offline, this supervised fine-tuning doesn't work so well because of some pathological behaviors they see. Let's see what specifically they see. So it looks like SFT collapses on the minor edits during learning and something goes wrong. I'll have to look into details about what is happening, but clearly what they find. And again, their experiments are on Gemini Flash version. I'm not sure how translatable these are to bigger models, but they see that it doesn't work. So what do they propose? So they propose a two-stage training approach. In the first stage, what they do is they give an input, sample the first output, the first 10 output, and then combine that with the correction prompt and get the second output, second turn output. Now, basically, in the first stage, they only train the output to correct the second stage. So the reward model that they are trying to optimize is on the second stage. And keep in mind, so they do this keeping the first output fixed. So what they want to do is train the model to fix errors of the first turn without changing the first turn. And this is what the without changing part is, this the KL divergence term that is here. Now, what they claim is this gives them a good starting point model. A good starting point model which has this ability to correct errors. And that this is what they pass into stage 2. Now, in stage 2, what they do is same thing, the sampling is the same. They compute reward on both the first term and the second term. So, and keeping the model outputs same as the original model. So they do not want to degrade the first attempt responses. So what this does is here we are trying to maximum reward over the first attempt as well, and also on the second attempt. So yes, the second attempt part is similar to what was before, but we also want to make sure that if the model can figure it out in the first attempt, we shouldn't degrade that. Now, how do they ensure that the results don't flip, right? If the first attempt was correct, the second attempt shouldn't flip. The way they do that is basically they add a bonus term, which is some factor times the reward of the second term negative the reward of the first term. So when it will flip, then the first term will get a lot of penalty, and that prohibits the large negative penalty prohibits the transition of correct responses to incorrect responses. That's kind of like roughly what the two-stage training process is. I'm not sure like how much this generalizes beyond beyond like two-tone conversations. It looks very specific to two-tone, but let's see. So here, the base model, let's say the accuracy of first turn was 50 and 40. They eventually get they increase the accuracy of the first turn because of this two-stage thing, and also the accuracy of the second turn. With SFT, you were only increasing the accuracy of the second turn, but you were also degrading the accuracy of the first turn. So this pairwise SFT is like you train basically a standard SFT on just the first turn and the second turn masked. Yeah, that's pretty much what I wanted to discuss with this paper. Anyway, interesting paper. Take a look if you're interested. The other big news, LLAMA 3.2 came out, and this is a bit exciting because they now went multimodal. So what they did is release two sets of models, an 11B, 90B, which are multimodal, and on-device models, like really small LLMs that are like 1B and 3B. So let's kind of like review what they've done. And before that, let me take a sip of coffee. Okay, and the crazy part is even the smaller models, they support a context length of 128K, which is fantastic. And they say they are like the models are very compatible to Claude 3, Haiku, at least the 11b and 90b ones. Okay, so that's all standard spiel. Let's see what else. If you can like suss out any technical details. And they say the 3.2 vision models are competitive with GPT-4o Mini, Claude 3 Haiku. I didn't know Haiku was a multimodal model, but I know. Okay, so for the vision part, they say so the base text model they've used are the llamas, and they say we trained a set of adapter weights that integrate pre-trained image encoder into the pre-trained language model. So okay, so this has cross attention layers that feed image encoder representation into the language model. So it's like a joint. So the architectures are not completely separate as it sometimes is in a bunch of vision models, or rather multimodal models. But it looks like this is a bit of like a blip 2 kind of training that they've done. But anyway, I don't know. I'll have to wait for the technical report or look into this load of the model to see the details of how the architecture looks rather. And so what excites me are the lightweight models. So it looks like they got these lightweight models using pruning and distillation, which is fantastic. So let's take a look at this figure. Let me zoom in. So it looks like they trained the 8B, 70B models, and they did some pruning, and okay, also some distillation to generate this. Okay, so the 1B and 3B basically come from the 8B and 70B models. Interesting. Okay, that's pretty impressive. And I was trying these out. These models are like not not bad. So um let's try them. Okay, they're also introducing Llama Stack distribution, some Stack API, some. Basically, they're eventually developing their framework where they'll serve models just like what AWS does and all the companies do. Okay, let's open it on the Hugging Face webpage. So Hugging Face also has a page on like how these models are and so on. I see a demo, and I want to try the smallest version. Okay, well, let's see if I can try something else. Oh, but before we go, this is the 3.2 billion, the 3 billion parameter model. And let's see, it uses GQA, which is standard nowadays. Anything else we can learn? I guess the architecture has to be closer to what the 8B one is, just less number of layers. So, okay, nothing too interesting here. That's fine. Let's try something. Okay, so let me. I like to ask these language models some multi-hop reasoning questions. So let's see. Let me zoom out a bit so that you can see what I am typing. Huh. This is a big chatbot area. Okay, so I'm gonna type it out and then I'll show you. Okay, so my question is, what is a country to the east of the country that is to the west of the country with capital New Delhi? So it's multi-hop because the capital of New Delhi is India. What is to the west of India is Pakistan, and then again to the east. So it should come back to be like India. So based on your description, blah blah blah, if forcing it, okay, that's. Wow, that's okay. So the answer is wrong, but it clearly did some reasoning. Okay, let's see if it can do some coding. Write me a Python code to convert literal into oh, sorry. Okay, so the code generation abilities are not so bad. This is pretty good. Like for a 3 billion parameter model, like can you imagine like I can't imagine the whatever BERT or GPT-2 to be like this nice. But you know, they weren't trained on so much data and fancy techniques. But that's all I wanted to talk about in this video. And I guess I'll see you guys next time. Thanks. Bye.